Well, after going through all those standard state calculations where we're looking up table values and working with table values only and working at standard conditions where 1 molar concentration of everything and standard delta G's and K values are at standard conditions. Now we're going to look at cell potentials at non-standard conditions. So now we're either at a different temperature, which isn't what we typically do with these. We typically still keep them at 25 degrees C or 298 K, but we change concentrations. For example, you can do some really great number crunching to calculate the delta G at standard conditions for biological processes. But your body doesn't have a lot of 1 molar concentrations of anything in it. And so we have to be able to calculate delta G and make sure it's going to be spontaneous for a particular reaction to go at body conditions. Maybe 10 to the minus 6th molar, 10 to the minus 8th molar, 10 to the minus 5th molar. So we have to come up with a way to correlate our standard calculating at non-standard conditions. And we did this in the thermal chapter. We calculated all of our delta G 0 values, and then we said, hey, what happens if we're not at standard conditions? And we had a correction for that. It's very difficult to maintain those standard conditions. You can create a standard condition galvanic cell, and it's great. 1 molar concentration in the beakers over here and over here, and as soon as you hook up the wires and juice starts to flow, it's no longer standard because you've allowed some electrons to move from one side to the other, so the concentration of the ions, one side it's going up, one side it's going down. Very difficult to maintain a standard cell. So most of our electrochemical processes that we have to deal with are actually at non-standard conditions. So we kind of use our standard condition E0 as a jumping off point and then correct for any other issues, just like we did for delta G. Back last chapter we had delta G at non-standard conditions was equal to delta G0, kind of our starting point, our theoretical value, plus RT times the natural log of Q. So in that chapter we change temperature and we can change our concentrations. For the most part, in electrochemical process, we're going to leave the temperature alone for our calculating. Okay? And we're dealing with Q. So we had this. We also know that delta G is minus NFE, and delta G0 is minus NFE0 for the cell. So we're going to plug those in up here. So we got minus NFE cell equals minus NFE0 for the cell plus RT times the natural log of Q. We just plugged in these two values with this stuff up here. And then we're going to divide everything by minus NF. So divide by minus NF. All the terms. That makes this E cell is E0 for the cell. This plus becomes a minus because we're multiplying by minus, or dividing by minus NF. So minus RT over NF times the natural log of Q. So if we know what E0 is for a cell, which is relatively easy to calculate, and we know what our concentrations are, so we know what Q is going to look like, we can pretty easily calculate E0 for the cell, because for a particular reaction holding temperature at 298, all of this stuff is a constant. N isn't going to change for a reaction if we increase or decrease the concentrations. So N, F, T, and R are constants for a given chemical process. But that's where we get our E cell, non-standard conditions, calculated based on E0 for the cell and our Q correction factor. All right, so this equation is called the Nernst equation. And it's kind of the Nernst equation in its raw form. It's actually not the form of this equation that you're going to see most often in textbooks. So we're going to do a little bit of work on this equation. You can use that one if you want. There's nothing wrong with using it. But the version that most folks use is the base 10 log instead of the natural log. The base 10 log version of this. So we're going to convert it to the log log. And we're also going to combine the constants up here. Think about back in the kinetics chapter, we had k this times k that divided by this k, and we just combine them all together into one single constant. So at 298k, T RT over F is a constant for all electrochemical processes, because R and F are constants anyway. T is a constant as long as we don't change from 298. So we're doing a couple things here. We're combining RT and F together, and we're converting to an log instead of a base 10 log. So Ecell is E0 for the cell minus 0.05916 volts. That's what you get when you put RT and F together over N. N is going to vary but be constant for a particular reaction, but you have to go case by case. Is it a 2 electron, 6 electron, 3 electron, or whatever? Times the base 10 log of Q. The 0.05916 is R times T divided by F, and the conversion factor between base 10 and natural log. There's a 2.303 conversion factor that you use to go between base 10 and natural logs. That's all combined together. This is the Nernst equation I'm going to use for all of my problems, and I encourage you to also. It allows us to calculate E for a cell at non-standard conditions, but still at 25 degrees C, because that's part of this number, at any set of concentrations. If you can write the equilibrium constant, you can calculate Q for it, you plug that in, and that's your non-standard E cell. One of the nice things about using the log version of Q here instead of the natural log is that as Q changes by a power of 10, the potential changes by 59 millivolts, or 0.05916 volts. That's the benefit of the log thing. You can kind of see if you're on the right track. I raised my Q value by a factor of 100, then the potential should change by 2 times this. For every power of 10 change, this much potential changes. Okay? I'm going to stop it there. We'll come back. We'll work an example or two based on the Nernst equation. So we'll be calculating E cell at non-standard conditions. It's really pretty easy because you should be fairly comfortable with calculating Q and just plugging in and chugging. Okay? See you in a bit.